Okay, let's go for video number 3/page 3 for this week, which is the root of the fundamental theorem of calculus, part 1. There are actually two parts, or some people call it like two different fundamental theorems of calculus. Our focus is going to be on FTC 1, and let's do it. So here's what FTC 1 is, and hopefully you made this connection from the first two videos, or at least had this thought. I was trying to drop lots and lots and lots of hints, but it says that f is a continuous function on a to b. Here's what we know about g of x, where g of x is an accumulator function defined by where the integral, the thing you're trying to integrate, is f from a to some number x. Between a and b, we know this about the g function. It's continuous on AB, it's differentiable on AB. Notice the subtle change in brackets. One's inclusive, one's exclusive, and g prime of x is f of x. So the big takeaway, hopefully, that you made from those first videos, or thing you thought, is that the derivative of this is the function we're integrating. And we can prove that really, really easily here. So that's what our goal is. So here's what I set up to do our proof, and how and why this thing is actually true. So I want to make a function g of x. So the graph here you have is of this function g of x. So let's just do this thing. So I want to do g of x plus h minus g of x. And since g is defined as this accumulator function from a to x, then g of x plus h would be you just plugging in an x plus h here. And g of x is just you plugging in an x there. No different than we did on those first little accumulator functions where g of 5 said plug in a 5 here. G of x plus h says plug in x plus h here. So g of x plus h minus g of x is basically telling you to, we can use our properties of integrals to just basically go from a to x f of t dt plus x to x plus h f of t dt minus the integral of a to x of f of t dt, and then we're kind of good. So what I'm basically doing is breaking up this one integral into two separate integrals, where if I'm going from a to x plus h, I'm splitting it up as starting at a, going to x, starting over at x, and then going to x plus h. Now why am I doing that is so that I can cancel this one and this one. So essentially integrating from x to x plus h is good enough to figure out what g of x plus h minus g of x is. So now the question becomes, well, what's the integral of x to x plus h, aka what's this thing equal to? So that's where our picture actually kind of comes in and why that's on your paper already. So if we're going to integrate from x to x plus h, we're essentially finding this area. That's it. So here's what I know about the integral from x to x plus h of f of t dt. I know that it is going to be less than or equal to this area. If we use the highest point in that window, that rectangle is going to overestimate our area. So I called the height of that highest point m. So the base of that thing should just be the base of this rectangle, and the base of that rectangle is x plus h minus x. So the base is just h, base is h, height I'm calling big M for the maximum value in that interval. And I can sandwich it in between. I know this rectangle is going to underestimate the area under that curve. So that has the same base h, and I'm calling its height little m, and now we're basically rolling. So now we have this thing jammed in between two things. So what we're interested in is what happens when h gets closer and closer to 0. If I shrink this window as x gets closer and or better yet, if I shrink this window as h gets closer and closer to 0, that's what we're sort of talking about. So what I want to do is I want to call m, I just want to call u the thing that makes the minimum. So instead of calling this m, I want to call this h times f of u. And I want to call this thing still h. And I want to call this f of v. I just want to call v whatever happens to make the max. Seems okay so far? Hopefully. So ultimately what I want to wind up doing is I want to see what happens when h gets closer and closer and closer to 0. So what I'd like to do is basically just divide everything through, or I want to just see this limit as h gets closer and closer and closer to 0. So the sneaky little thing is as h gets closer and closer and closer to 0, we start looking at a smaller and smaller region. So as h trends to 0, we start talking about this is x plus h now. So now we're just looking at this part of the curve, and we only care about finding this region. And now when we're in this region, this is going to be the new u, because it's the low point. So this is going to be the new little m. And this is going to be the new big M, because it's the high point, as h gets closer and closer and closer to 0. Seems okay? Hopefully. That's kind of the idea here. So here's what else I want to do. I want to take this part here, and I know that that part here is this g of x plus h minus g of x. So we can rewrite this as h f of u is less than or equal to g of x plus h minus g of x f of v. And again, we're looking at this thing as h gets closer and closer to 0. And the idea is these regions sort of just we're shrinking the region. Now this expression, which you maybe were really, really confused where it came from at the beginning, is here because it should look strikingly similar to, or familiar to something you've seen before. And that thing is, that's like the numerator in the definition of the derivative. What it's missing is that h in the bottom. So what I would recommend we do is divide everything through by h. These cancel, and we're pretty much okay. So what we officially get to now is, I need to erase this so we have a little more room here. Once we divide by h, we should wind up saying that f of u is less than or equal to g of x plus h minus g of x over h less than or equal to f of v. And the key thing here is that's not quite the derivative, which is what we think is true. That is the numerator and denominator of the definition of the derivative. It's just missing that limit part. That's why I kept referencing before the limit as h goes to 0. So this middle limit is actually our easiest one. That is g prime. It's just these other limits are kind of weirder. So again, if we go back to the area picture, we're thinking about this thing as h gets smaller and smaller and smaller. And as h gets smaller and smaller and smaller, you're talking about a smaller portion of the curve. If we shrink h to be small enough, we eventually just start talking about only this sort of part of the curve. So u and v, the thing that produces the min and produces the max, as our window gets smaller and smaller and smaller, we're talking about less and less and less of the graph, to the point that the graph is basically just like one little dot. And the thing that makes the max and the thing that makes the min, when the graph is like the shortest possible window possible, are the same thing. So what's weird are these two limits. These two limits are both f of x. If we shrink the window down small enough, the only value that's relevant here is x, and x is responsible for both producing the min and the max. So what we've got is that f of x is less than or equal to g prime of x, which is less than or equal to f which kind of only makes sense if G prime is equal to F. Been a little while since we've done the squeeze theorem, but that's officially it. We have this big, wonderful, exciting discovery, and it's that G prime of X is equal to F, that the derivative of your function is equal to the function you're trying to integrate when it's defined as an accumulator function. And that is called the fundamental theorem of calculus, or FTC Part 1.